if you're building modern AI, you know the ground has been shifting under our feet. We've really moved past that um, classical batch supervised learning model.
Oh, absolutely. The whole big data era, with frameworks like Spark, was built on these static computation graphs, great for fixed data sets.
But that's not the world we live in anymore.
Mm.
The frontier is now, well, it's dynamic, it's interactive, especially in reinforcement learning.
And that's the core system challenge, isn't it? RL needs this constant feedback loop with an environment. The computation graph is, by definition, unpredictable.
So the very nature of the next task depends on the result of the current task.
Exactly. And this forces this really tight integration of three completely different kinds of workloads,
We're talking about simulation, distributed training, and then real-time policy serving.
all in one system. And if you try to stitch together specialized systems for each one, the whole thing just falls apart.
The integration overhead, the data movement latency, it just becomes prohibitive.
It's a huge systems engineering problem. You have tasks that last milliseconds, like a simulation step, and others that run for hours, like a full training iteration.
Plus, the resource needs are all over the map. CPUs for maybe millions of simulation tasks, and then you need GPUs or TPUs pinned for the heavy policy updates.
No existing system could handle that loop efficiently.
And that brings us to our deep dive today. We're going to unpack the architecture that was built to solve this exact problem, Ray.
From the foundational paper, Ray, a distributed framework for emerging AI applications.
We're going to see how they designed a general-purpose framework to unify these next-gen requirements. And here's the number that tells you they succeeded.
I think I know the one you mean.
Ray's dynamic execution engine scales beyond 1.8 million tasks per second. That single metric is just validation of their entire approach.
It really is. And to get why that number is so important, you first have to break down what RL really demands from a system.
Okay, let's do it.
So first, you need massive, fine-grained simulation to generate all your training data, your trajectories. And that means you need very low overhead task management.
Right. And then you need robust distributed training to actually improve the policy on that data. That's coarse-grained, resource-hungry, and uses things like all reduce.
And then there's the third piece, the one that's often overlooked, policy serving.
Where you have to render actions in real time with millisecond latencies.
Exactly. And the sheer disparity between these things is what breaks traditional frameworks. If you just assume simple 5-millisecond tasks on a decent-sized cluster, you immediately need a framework that can handle over 1 million tasks per second just to keep the hardware busy.
So the core challenge is unifying this stateless, fine-grained simulation with stateful, coarse-grained training. Ray's solution starts at the programming model.
It does. They built it around a dynamic task graph that supports two key primitives at the same time, tasks and actors.
Let's start with tasks.
The tasks are the simple stateless part. They're just remote function calls that operate on immutable data objects.
And that immutability is key, right? It guarantees idempotence.
Precisely. If a worker fails, you just re-execute the task on its inputs. No side effects, it's clean.
Perfect for data processing, or those massive parallel simulations you mentioned. The API is simple, f.remote, gives you a future, ray.get, pulls the value.
And it lets Ray's scheduler be really smart about data locality. It can move the computation to the data, not the other way around.
But like you said, you can't run a parameter server or a big iterative training loop with just stateless functions.
You can't. And that's where actors come in. Actors are different. They're explicitly created stateful processes.
So they have internal state that persists between calls.
Exactly. Their methods execute serially, so the second method call depends on the state left behind by the first. This is how you can wrap, say, a third-party simulator or manage a model's weights on a GPU during training.
Okay, but hold on. If Ray's whole fault tolerance model is built on this beautiful stateless task graph and immutable data, how do you jam these messy stateful actors into that model and still get that lineage for recovery?
That is the most clever part of the programming model. They call them stateful edges.
Stateful edges.
Yeah. So when you call methods on the same actor one after another, Ray doesn't see them as isolated events. It draws a stateful edge between them in the graph.
So it's explicitly tracking the dependency on the actor's hidden mutable state.
It is. And by doing that, it maintains a complete lineage. The recipe for how that actor's state evolved is always recorded.
So if an actor dies mid-training,
Ray knows exactly how to rebuild it. It can revert to a previous state or checkpoint and re-execute the method calls from there. This is what makes using cheaper, transient hardware like spot instances actually viable.
so smart. And beyond those two core primitives, they added a couple of API features specifically for the chaos of RL. The first one is ray.wait.
Yes, which is so important. Unlike ray.get, which blocks until everything is done, ray.wait returns as soon as the first, say, K results are ready.
So for asynchronous algorithms, you can immediately start processing the fastest simulation results instead of waiting for the slowest ones.
It dramatically improves resource utilization. And the second thing was the ability to specify granular resource requirements.
Like, this task needs 1 GPU, but these other 100 tasks just need a fraction of a CPU.
Right. And that lets the scheduler make very smart decisions when you're running GPU-intensive training and CPU-intensive simulation at the same time.
Okay, so that's the programming model. Now let's get into the system architecture that actually hits that 1.8 million tasks per second number.
The core principle here is scalability through statelessness. All the workhorse components in Ray's system layer are designed to be stateless.
Which means they can be horizontally scaled and they're easy to make fault tolerant. But if they're stateless, where does all the control state actually live? The lineage, object locations.
It all lives in one place, the Global Control Store, or GCS.
The GCS.
Think of it as a decoupled, centralized metadata hub. It holds the entire computation lineage, it knows where every object is and how big it is, and critically, it's designed for scale itself.
How so?
It uses sharding to distribute its data across the cluster and chain replication to make it fault-tolerant.
And the decoupling is the genius part.
Yeah.
By putting all the durable state in the GCS, the actual execution scheduler doesn't have to worry about it. It's not a bottleneck for every data transfer or recovery event.
Exactly right. The GCS lets the scheduler do one thing and one thing only: schedule tasks. It keeps the overhead incredibly low.
Okay, but even with the GCS, you still have the classic problem of a centralized scheduler becoming a bottleneck, right? How do they avoid that?
They used a really interesting two-level design. It's a bottom-up distributed scheduler.
So there's a local scheduler on every single node.
Yes. And the bottom-up logic is simple. When a task is created, it first goes to the local scheduler. That scheduler tries to place it on the local node.
And only if that node is overloaded,
Right.
or maybe doesn't have a GPU that the task needs.
Only then is the task forwarded up to the global scheduler.
That makes sense for local tasks, but what about the latency for tasks that do have to go to the global one?
They make that global decision incredibly efficient. The global scheduler doesn't just look for a free slot, it calculates the estimated waiting time for the task on different nodes.
And that's more than just queue lengths.
Oh yeah. It's the queue time plus the estimated time to transfer all of the task's remote inputs, and it gets that input size and location data directly from the GCS. So it's always making a locality-aware decision.
And the data itself, where does it live?
In the in-memory distributed object store, on each node, it uses shared memory and Apache Arrow to allow for zero-copy data sharing between tasks on the same machine. That's a huge performance win.
And since objects are immutable, fault tolerance is just handled by the GCS telling a worker to re-execute the lineage to recreate a lost object.
It's all very seamless.
Okay, let's get to the numbers that prove all this works. The headline, again, near linear scalability, peaking over 1.8 million tasks per second on 100 nodes.
Undeniable proof of concept. And they also showed that their locality-aware scheduling wasn't just a nice-to-have, it was mandatory.
What do you mean?
Turning it off caused a 1 to 2 order of magnitude latency penalty for common data sizes. Just massive. Even the GCS recovery was fast, under a 30-millisecond delay for clients during a failure.
But the result that really jumped out at me was about the distributed primitives. For all reduce, a critical bottleneck in training.
I know. Ray actually outperformed OpenMPI.
By up to 2x for large objects. A general-purpose framework beat a super-specialized, highly optimized communication library.
That's a wild result. How?
The paper suggests it's because Ray uses multiple threads for network transfers, saturating the link, while OpenMPI often uses just one. But more importantly, they showed how fragile that performance is.
What did they do?
They injected just a few milliseconds of artificial delay into the scheduler, and the all-reduced performance dropped by nearly half. It proves that the scheduler's ultra-low latency is absolutely essential.
And this performance held up against other specialized systems too, right?
It did. For distributed training, their synchronous SGD was on par with Horovod and within 10% of distributed TensorFlow.
Which proves the general API is powerful enough. You don't lose anything.
And for policy serving, in that co-located client-server setup, Ray had an order of magnitude higher throughput than Clipper, a dedicated serving system.
Wow. That's the shared memory abstraction paying off.
It is. But the real win, the most impactful result, I think, came from the complex real-world RL algorithms.
The PPO results, proximal policy optimization.
Yeah. Ray's implementation beat an optimized MPI version while using fewer GPUs. And the key was that heterogeneity-aware scheduling.
Ah, so they could use cheap CPU-only machines for the simulations.
Exactly. And keep the expensive GPU instances just for training. When they combine that with using cheap spot instances, which the fault tolerance enabled,
Let me guess, a huge cost reduction.
they estimated an 18x cost reduction. 18 times. That's not an optimization, that's a paradigm shift.
And for the really demanding stuff, like evolution strategies, Ray just scaled to a different level. It went up to 800 and 192 cores.
While the specialized reference system they tested against failed after just 1024.
And because of that scale, Ray solved the humanoid V1 task in 3.7 minutes. The previous best was 10 minutes.
So, to sum it all up, what Ray delivers is this powerful combination of flexibility with the task actor model, massive performance, and crucially, ease of use from the transparent fault tolerance.
It just removes this enormous systems engineering burden. The value proposition is so clear. As a researcher, you can stop fighting with infrastructure and focus purely on your algorithm. Ray handles the rest.
And it all comes back to that one core architectural decision we talked about, decoupling the global control store, the GCS, from the execution logic.
That logically centralized but physically sharded, durable control plane is the key that unlocks everything else. It lets the execution layer be stateless and fast.
Which brings us to the final thought for you to chew on.
I think the provocative idea here is to take that GCS-centric design principle outside of AI and RL. Think about how many traditional data flow or graph processing systems are still built around a monolithic master node that does both scheduling and state tracking.
And that master always becomes the bottleneck.
Always. Ray proved that the path to true scale and dynamism is to pull that durable control state out of the scheduler and into its own scalable, fault-tolerant service. What other systems could be revolutionized by that one simple but profound idea?